Okay, let's look at section 4.3, which talks about L'Hopital's rule. Right? L'Hopital's rule is a technique to evaluate the limit, usually have in a fraction form, when the numerator and denominator either goes to both 0 or goes to infinity. Then we can actually take the derivative of the numerator and the derivative of the denominator, then take the limit. And that limit actually gives you exactly the same limit as the original limit, right? So it goes kind of like this. So if you want to find the limit of, say, function f of x over another function g of x, so you have a quotient, and x goes to some number, say a, right? And if the numerator goes to 0 as x approaches a, and the denominator approaches 0 as x goes to a, then we can do this. This limit is going to be exactly the same limit as the limit of f prime of x over g prime of x as x approaches a, right? And you have to be careful. We're not using the quotient rule here. We're taking a derivative of the numerator by itself and the denominator by itself, right? And another case is this 0 over 0 is called the indeterminate form, and this is a first indeterminate form. And the second kind is when you have infinity over infinity. So if numerator approaches infinity, it could be positive or negative, and the denominator also goes to infinity. So when you have infinity over infinity, you can still apply L'Hopital's rule here. All right. So let's start with a motivational example. All right. So we've seen this kind of limit, a limit of x squared minus 1 over x minus 1 as x approaches 1. And you can see that if you plug in x equals 1, you can see that the denominator approaches 0. And 1 squared minus 1, numerator, approaches 0. Right? So before L'Hopital's rule, what we did was we factor out, since the 0 over 0 indicates that there's going to be a common factor on top and bottom. So we want to squeeze that out. So we have limit, right? So we can factor x squared minus 1 as x minus 1 times quantity x plus 1, and over same denominator, x minus 1 as x approaches 1, right? Then we can cancel factor x minus 1 on top and the 1 on the bottom. Then we can plug in, and you see that if you plug in x equals 1, you get 1, and you have plus 1. So limit is going to be 2. Right? So this is sort of the old method. So this is the old method. Right? So the new method is when you have 0 over 0, we can actually take the derivative. So the new method is going to be, so maybe I'll write it in maybe a different I'll just use the blue here. So here, using a L'Hopital's rule, right, we can actually take the derivative of the numerator. So derivative of the top is going to be 2x. And the derivative of the bottom would be just 1, right? Then plug in 1. So you have a 2 times 1 over 1 is obviously 2, right? So this is the new method. So this is the L'Hopital's rule, right? But you can see that you get exactly the same answer. All right, so this method is effective if you have something like this one, right? So second example, limit e to the x minus 1 over 2x as x approaches 0. Right? Then you can see that the denominator, 2 times 0 is 0, so approaches 0. Numerator, e to the 0 is 1 minus 1, so numerator also approaches 0. Right? So we want to factor out the common factor, but you can see that it's going to be very difficult to squeeze out some common factor from e to the x minus 1. Right? So in that case, the L'Hopital's rule comes in very handy. Right? Let's go ahead and apply L'Hopital's rule here. L'Hopital's rule. Right? So we can just take the derivative of the numerator. So derivative of e to the x is e to the x, and derivative of negative 1 is 0, because negative 1 is a constant. Right? Derivative of 2x is going to be 2, right, as x approaches 0. Right? Then you see that if you plug in 0, e to the 0 is 1 over 2 is 2. Right? So that is the limit by L'Hopital's rule. Alright? That's it. I hope that this was clear. And the following example we're gonna have some example involving infinity over infinity as well. Right? That's it. I hope that this was clear.